In this video, we'll go into the errors that come about when using Euler's method for solutions, or approximate solutions, and sort of where they come from. So we saw that in general with the previous examples we've done, and with stuff that you will write out on your own, that sort of the farther you step away from the initial value, the further you get from the solution. In general, right, you're making errors at every step, so you're going to get farther away as time goes on. Is that necessarily the case? Well, the answer here is actually no. It is not necessarily always the case that you'll get farther away from the solution as you go. And the main reason for that is this all comes from linear approximation. The entire idea of Euler's method is that we're going to approximate the solution curve by its tangent line, which we know from the differential equation, and then step that forward over and over again. So it's possible for the sort of errors we make at every step to cancel out over time. For the last two examples, this did not happen. The issue was basically that at every step, we always made an error in the same direction. So in both cases previously, our approximation was always smaller than the solution at every step. And by smaller, I mean smaller than the actual solution. There's arguments to be made there about concavity and stuff about this function that way. But the point here is, with our approximation smaller at every step, we continuously got further and further and further away from the actual solution because we were off by a little bit, and then from that we're off by a little bit more, and it sort of built up over time to get us far away from the solution. If you don't have that, then stuff could cancel out and you could end up close to the solution over time, even if you start farther away. Another way to think about this is that when you make this error, you're sort of jumping onto a nearby solution curve for a different initial condition. Right, so if you draw a little picture with this, for the first example, we started at y of 0 equals 1. So we started here, and we took our first step, and we ended up, say, here. Which was fine, that was our tangent line, so that was great. But the point was, the actual solution did not go there. The true solution went up this way, and it was higher than where we were before. So we should have been here, but instead we were down there. Being down there is now sort of equivalent to actually not having this as the initial condition, but instead having, say, some point down here as the initial condition that actually comes up to meet this point. So we've jumped to a nearby solution curve. And it's nearby in the sense that, these two things are pretty close here, they're pretty close here, it's not too bad. But the issue is this compounds over time. So I take one more step from my condition here, and say I end up over here, because that was my tangent line, great. But now I'm off of the green curve, which I was on before, and I'm even further away from the orange curve, which is where I should be in the first place. And so these things continue to stack up and go on and on and on. You're jumping to nearby curves, and provided the nearby curves get further away as t goes on, this is going to end up causing a problem for this method in staying nearby without super, super tiny step sizes. Let's see this in the context of an example. So we're going to take two different linear ODEs here. You've got equation 1, y prime minus y equals 2, and equation 2, y prime plus y equals 2. And we can solve these out to get to general solutions, which if we do, we'll get for the first one, y of t is minus 2 plus c e to the t, and for the second, y of t is 2 plus c e to the minus t. Now what's going to happen here if I sort of go out positive in t, look at these solutions? Well, for part 1 over here in orange, for different values of c, the solutions grow farther and farther apart as t goes on because they're multiplied by this e to the t term that's getting bigger as t grows larger. So as t gets large, solutions with different c values or different initial conditions get further apart, because this e to the t term is going to grow as time goes on. To contrast that, for equation 2, the opposite happens. No matter what the c value is, the solution will converge to 2 as t gets large because e to the minus t is going to 0. So in this case, as t gets large, the solution converges to 2. And what that means in this context is that for different c values, the graphs actually stay close together or get close together as time goes on. So what that means is that jumping to a different curve or a different c value isn't really going to hurt me for this second case. Because no matter where I go, the solution is always converging into 2. I might be off by a little bit, but eventually I will still get to 2 no matter what I do, because jumping to different curves doesn't sort of hurt me in that context. Whereas in the first case, getting on a different curve goes far away. So the examples we did before where we started losing accuracy really, really quickly were more like this one, where nearby c values diverge or go away from each other as t goes big. Whereas examples where that doesn't happen and where Euler's method works for a very large step size are things like this second example, where the curves that are nearby really stay nearby and don't really run too far away as t gets big because they're all converging to something. That being said, smaller steps is always better and has more guaranteed accuracy, but there are examples like this where you don't necessarily need that small of steps, or you could get good accuracy even with a fairly large step size because of how the solution curves behave.